In this lesson, we're going to look at some examples of how vectors are used in the real world, how we can apply them to real life situations. Two of the more common things are forces and velocities. Force is something we usually use in physics. It's the amount of work you do when you're moving an object. You're pushing, you're pulling, you're using forces. And velocity, we've talked about that back when we did bearings. We had planes flying and boats moving and things like that. And both of those involve directions and magnitudes. A certain speed in a certain direction, or a certain amount of force in a certain direction. And so just some applications here today. So we have Buffy and Chloe, and they're trying to push a crate across the floor. So we've got ourselves a crate. Okay, Buffy pushes with a force of 50 newtons west, and Chloe pushes with 35 newtons south. Okay, newtons are the way of measuring our forces, just so we're all on the same page with that. So we think of this as a compass in the middle of the box. Okay, Buffy is pushing with a force of 50 newtons towards the west. So she has a vector going this direction, and it's 50 newtons. Chloe is pushing with 35 newtons south. So hers is going to go down here, and they're going to meet at a nice right angle. In fact, if you look at the diagram, you can see the right angle right there, right? I want to know the resultant force. Now from yesterday, we said that the resultant occurs when our two vectors are added together. So we have to use one of our two methods, either tip to tail or the parallelogram method. Because my vectors are joined at the tails, the parallelogram method is a good choice. So I'm going to complete my parallelogram, which in this case happens to be a rectangle, and my resultant will go at the tails to the heads. And we'll call it R for resultant. Okay, now it's asked for the resultant force. Forces have directions and sizes. So the first thing I'm going to do is I'm going to figure out the size. Now, I can translate my 35 to the other side to think about the idea of Pythagoras, and that will allow me to solve this question pretty quickly. Okay, r squared equals 50 squared plus 35 squared, the idea of Pythagoras, as I said. Or in other words, r is just whatever the square root of 50 squared plus 35 squared is, the magnitude of your vectors, your components, if you will. Okay. Now, if you use our calculators and square root those two things, you should get 61.03 newtons. Okay, so I got myself a magnitude. The other thing I need is I need a direction. So the direction that I'm going to find is this one here inside my triangle. I'll call it x. Again, I can use my ideas of right angle triangles, Pythagoras for size, and SOHCAHTOA for angles. Based on this x, this could be my opposite, this would be my adjacent, I can use tan. So the tan of x equals 35 over 50, or in other words, x is the inverse tan of 35 over 50. You can punch in your calculator just the way that looks. We're going to get an angle measure of 34.99. Okay. So when I go to answer my question, the resultant force is 61.03 newtons. And now I have to give a direction. So I have to do it in terms of bearings because that's the kind of question I was given, right? Give me west and south and things like that. So think about where that x is. It's between west and south. In fact, it's at an angle of west 34.99 south. And remember with bearings, we can write them in any one of three ways. I can start west and south, south and west, or use my bearing from north. So it's a nice simple application of how we can actually use vectors. Things going in certain directions for a certain size. Let's try another one. Example 2, slightly trickier. We have an object being towed by two ropes. The directions of the forces of the ropes are north 20 west and north 30 east. Okay, so we got some sort of object. It's being towed by a rope. Okay, here's our compass. We know one of the ropes is north 20. Oh, sorry, north 20 goes the other way. North 20. And the other one is north 30. Okay. The resultant force is 1,000 newtons due north. So let's stop and think here for a second about a resultant force. How do we get a resultant usually? I get resultants, I'm just going to move this, okay? I get resultants by adding my two vectors together, tip to tail. Well, right now they're tail to tail, which means I have to complete the parallelogram. So if I were to complete the parallelogram, the resultant would go from the tails straight north, because that's what it told me in the question, to the heads. That's my resultant. I was told it's 1,000 newtons. We're asked to find the magnitude of the tension. In other words, how much force there is in each rope. Okay, so I'm going to label them force 1 and force 2. So let's call this rope 1.
Would Mrs. Campbell contact the office, please? Mrs. Campbell, could you come to the office?
Okay, which in our parallelogram method is, this is also force 1, right? Now to do this one, I know the resultant. I'm asked to figure out the initial forces. I can actually use the sine law here. I know that the sine of 30 is going to match up with force 1. I also know that my 1,000 Newton resultant is across from this angle. And here's your thinking thing for this one. Hopefully you see a C pattern. Because in a C pattern, the angles on the inside add up to 180. So this angle over here has to be 130. Okay, so I can say the sine of 130 matches up with 1,000. We can cross multiply and solve this. So force 1 times the sine of 130 equals 1,000 times the sine of just 30. So force 1 equals 1,000 sine 30 over sine 130. If we put that all into our calculator, we should end up with 652.7 newtons, according to mine. And there's our force 1. I can do basically exactly the same thing for force number 2. And force number 2 is across from that angle up there. And because our triangle adds up to 180, this little bit has to be 20, or you can use your Z pattern if you want to also. So we can get the sine of 20 across from force 2 equals the sine of 130 again over 1,000 Newton resultant. And we're going to follow the exact same procedure. We're going to cross multiply and solve. So I'll just skip the step for a second here. We'll end up with 1,000 sine 20 over sine 130. It's the exact same procedure we did up above. Cross multiply and solve. You should get 446.5. Okay. So again, we can use the ideas of resultants to figure out unknown things. Okay. Make sure you're doing vector. Okay. Third example. Yeah, we're just some warm-up things here of how we can use resultants in the real world. So we got a plane. It's headed north 30 east. Okay, so we need ourselves a compass. North 30 east. So start north, go 30 to the east. It's going 800 kilometers. Here's your magnitude. It encounters a wind of 75 kilometers blowing in the direction of southeast. Okay, so we get to the end. Our plane's trying to fly, but the wind's pushing it towards the southeast. So at the end of our vector addition, I have a wind. Now, the wind is 75 kilometers an hour. And the nice thing about southeast is it means it's halfway between south and east. In other words, this angle here has to be 45. I want to know the resultant velocity of the plane. So my resultant is tip to tail, which my diagram already is. So I can go from the tail of the first to the head of the last. And that would be our resultant. So what do I need to solve this problem? Well, if I were to know the angle between the two known sides, in other words, if I knew all of this, I could use the cosine law. So let's think about the idea of two compasses. When you have two compasses, they have to be parallel, which means there should always be a Z pattern. And hopefully you see the Z pattern we've just created. A 30 here means there has to be a 30 here. which means that entire angle, the blue one we drew originally, has to be a total of 30 plus 45, or 75 degrees. Knowing that, I can use my cosine law. So in other words, r squared equals a squared plus b squared minus 2 times a times b times the cos of the angle, which happens to be 75, between them. And I can punch it all in my calculator. That can be r squared, and then square root it, and we should get 783.9. Now that's the magnitude of the plane. The plane's not going quite as fast as it was. It's running into the wind a little bit. The wind is slowing it down. But when we're talking about velocity, velocity needs a direction. So the plane was trying to fly north 30 east, but it ended up going a little bit further to the east than it wanted. How much further? Well, that's the angle there. So how can I find that angle? Well, we can go back to the sine law. So I know that my 75-degree angle is across from the resultant, which is 783.9. And the angle that I want, x, is across from the wind, which is 75. And we're going to solve this by cross multiplying. So 75 sine 75 over 783.9 comes up to sine x. Punch it all in your calculator. Then we'll take the inverse of whatever you get there. And if you do it right, I end up with 5.3 degrees. Okay, let's answer the question. The plane's velocity is, well, the speed is 783.9 at, we need a direction. Now remember, the direction was 30, right? The angle here to here was 30, but it's gone a little bit further to the east, an additional 5 degrees. So the angle that it's going at is actually north 35.3 east. The 30 it started with plus 5 additional degrees because it's been pushed off course. Okay, that's how we can do some ideas of how we can use results in the real world. Okay, so that's the first half of our lesson. Second half of our lesson, let's start thinking about working backwards. Sometimes we want to balance out what's been happening. We don't want to go off course. We want to stay on course. Where should we aim instead? We don't want our object to move. We want to stay still. How much force do we need to exert and which angle? So these ideas reference a thought called the equilibriant. A single force which when applied to an object would prevent it from moving. It stays in the exact same spot. It counteracts what's been happening to it. And we call it the equilibriant. It's the exact same magnitude, but the exact opposite direction as your resultant. So we went back to the very first example for a second. We looked at Buffy and Chloe, and we did not want them to move the box. We would have to apply a force in the opposite direction as a resultant. We'll call that E for equilibriant. And the equilibriant would be 61.03 newtons. But it would be the exact opposite direction that we started in. So in this case, instead of going west 34.99 south, okay, notice this angle here would be the same because they're opposite angles, right? So it's still 34.99. But instead of being west and then south, it would be east and then north. Okay, we're just going to write that in. Okay, so it would be 61.03 newtons at east 34.99 degrees north. The exact same size, but the complete opposite direction. That's what an equilibriant does. It balances out what we started with. And let's try an example of one of these. We have two forces of 20 and 30 newtons making an angle of 120 to one another. I want to figure out the resultant and the angle makes it a 30 newton force, and then do the same thing but with the equilibriant. So let's start by drawing. I got force 1, it's 20. Force 2, it's 30. I know there's an angle of 120 between them. To do resultants, I have to do vector addition. I don't have vector addition right now. They're tail to tail. So I have to complete the parallelogram. Complete the parallelogram. My resultant goes up the middle. Okay, we can use our C pattern to figure out the angle in the corner over here. It's got to be 60. So we're back to that cosine law, right? R squared equals 20 squared, and this is 30. 30 squared, 2 times 20 times 30 times cos. Angle between them, 60. Into your calculator, square root it. You end up with 26.5 newtons. Okay, I also want to know the angle it makes with the 30 Newton force. So the 30 Newton force, that's this angle right here. Call that x. This is 20. Okay, this is, what else do we know? Oh, this is 60 up here. Okay, we can figure out all those different things. So I want to know the x. What do I know? I know that x is across from 20. I know my 60 degrees is across from the resultant, 26.5. I know I can cross multiply and solve. So sine x equals 20 sine 60 over 26.5. Into your calculator, inverse function, and you should get 78.2 degrees. Okay, and that's 78.2 with the 30 Newton force. Okay, so let's look at the equilibrium now. Part B. Determine the equilibrium and the angle makes us a 30 Newton force. So the equilibrium is going to balance out our first force. Well, the nice thing about that is our equilibrium has to be the exact same size. So for B, the equilibrium has to be, what's our number here? 26.5 newtons. Okay. Oh yeah, tricky part is I have to figure out the angle makes us the 30 Newton force. So the 30 Newton force and equilibrium meet right here. Now the good news is, in the previous question, I figured that x was 78.2. So how can I figure out what y is? Well, x and y make a straight line. So together they have to add up to 180. So y will equal 180 minus 78.2, or 101.8 degrees, with the 30 Newton force. Okay, you kind of need to know the resultant to be able to figure out the equilibrium. What happened when you added them can be counteracted when you point the opposite direction. So a little bit more about equilibrium. Our whole idea about equilibrium is that these vectors have to balance each other out. The three vectors have to work in a group to counteract each other. So let's say I had vector A and it's 4 centimeters right. So A goes this way, 4 centimeters. And I had vector B and it goes 6 centimeters left. Okay, this is right here, right? What would I need vector C to do to create a state of equilibrium, to balance each other out? Well, C would have to be added to the end over here to balance it out. Like think about a scale. And how big would it have to be? Well, it would have to be 2 centimeters. So I have 6 on one side and 6 on the other side, just like a balancing scale. Now that's kind of obvious when you're working in tandem, if you want, in a straight line. But what happens if they're not in a straight line? What if they're at angles to one another? So we can create a state of equilibrium if we can take any two vectors, join them together tip to tail, and balance it out by completing the triangle. Okay, so let's say I had vectors A and B and C here. I want to be able to add them out and create a triangle. So I obviously can't add A and C and balance that with B. Didn't work. Okay, well, if I took A and B and tried balancing out with C. Oh, sorry, I gotta move here. Move that one. A and B and try and balance out with C. Well, that didn't work. Okay, I gotta figure out the combination that when I put them together, so B and C, can be balanced out by A. Okay, so I can create an equilibrium by using A and B and balancing it out with C. So here's a little rule for you. You don't want to draw triangles over and over and over again. In order to form a triangle, in other words, equilibrium, the sum of any two sides must be at least equal to the third side. Okay, so we look at some numbers for a second here. 4, 12, and 20. Why can they not be in equilibrium? Well, if I tried drawing a 4 and a 12 and a 20, why could they not be in equilibrium ever? Okay, well, if I were to add 4 and 12 together and put them in tandem, can they balance out something that goes 20? Oh no, they're not equal. I can never do that. It's not possible. They have to be able to balance each other out. And in this case, they can't do that. But if I look at the next one, 3 forces of 7, 12, and 15, they could be in equilibrium because 7 and 12 is bigger than 15. 12 and 15 are bigger than 7. And 7 and 15 are bigger than 12. Any combination will be at least as big as the third one. So I want to figure out how they can be in equilibrium. What angle do they have to be at? So let's give them a draw here. We got one at 7. We got another one at 12. We don't know what angles they're at, okay? And we know the third one, to balance it out, is 15. So together they make 15. I want to figure out the tail-to-tail angle formed by the two smaller forces. Okay, so how am I going to do this? Well, the two smaller forces aren't connected tail to tail right now, are they? To balance them out, I had to make it into a triangle. So where is the tail to tail angle? Well, if I think about it, I can do my parallelogram idea. I hope you could agree this is also 12 newtons. The tail to tail angle is this one, between the two small forces. The nice thing about that one is it's related to the tip to tail angle because of this C pattern. So if I can figure out y, then I can figure out x. How can I figure out y? I can use the cosine law. Okay, I'm going to use the cosine law for the angle this time. So we're using the version that's set up for angles. Okay, so I want to figure out the y value here because that's one I can figure out, okay? So we'll do 7 squared plus 12 squared minus 15 squared over 2 times 7 times 12. Okay. In our calculator, we'll figure out the top part. We'll figure out the bottom part separately. I get negative 32 over 168. I'm going to take the inverse of that. And hopefully, if you take the same inverse that I did, we end up with a y value of 101 degrees. And that's the tip-to-tail angle. We want to know the tail-to-tail angle because when two forces act against each other, they're always tail-to-tail. So where is x going to come from? X will be 180 minus the 101, or in other words, 79 degrees, tail to tail between the 7 and 12 Newton forces. Okay, and that's a little bit of how we can use these vectors in the real world, applications, resultants, and equilibriums. Okay, homework questions, you try. So be careful in question 16. You have to change the weight to a force. We can always do that by multiplying by 9.8 before you can actually attempt the question.